You are given an integer matrix. From any cell you may step to a neighboring cell with a strictly larger value, moving only up, down, left, or right without leaving the grid or revisiting a cell. Find the length of the longest such path, counting cells. Example 1, the longest route uses 4 cells. Start at the bottom 1, step left to 2, climb to 6, then finish at 9 in the top left corner. Example 2, another length 4 path. Start at 3 on the top left, cross 4 and 5, then step down to 6 on the right. We initiate our exploration by launching a depth-first search from a single cell. For this example, we begin at 6. We scan our surroundings, identify strictly greater neighbors, and follow one valid upward path to 9. From this 9, we trigger a new neighborhood check. Because every surrounding direction fails our strict increasing rule, we hit a dead end, forcing this cell to return a baseline path length of 1. As our recursive call stack unwinds, it passes information backward. That score of 1 from the 9 travels in reverse back to the 6, which adds 1 to account for its own step. A cell must evaluate all valid directions before locking its final score. We check our remaining neighbors. While down and left fail, the rightward step to the 8 yields an alternative path of 2, confirming our max score is 2. Watch where a naive approach breaks down. Without memo, left 6 is reached from 2 directly, and again from 1 through 2, forcing the algorithm to rerun the exact same deep recursion all over again. To break this bottleneck, we introduce a matching memo table cache. The moment any cell finishes evaluating, it saves its score. Now, when a new path approaches an explored state, we stop the recursion dead, pull the saved score instantly across the screen, and skip the redundant work entirely. We translate our intuition into code by initializing a matching memoization matrix filled with zeros, serving as our tracking memory cache. We loop through every coordinate on the board, launching our depth-first search engine from every single grid position to guarantee we intercept the global maximum runway. At the entry point of our recursive function, we immediately protect our boundaries by checking our cache table. If the value at our current row and column coordinate is anything other than 0, we halt the recursion dead in its tracks and instantly return that pre-recorded score. If the cell is unvisited, we iterate through its 4 cardinal neighbors. We enforce our boundaries and apply our strict rule. We only trigger a recursive call if the adjacent cell contains a strictly greater number, gathering the maximum runway length available among all valid directions. Finally, we lock down our answer. We take the maximum branch score discovered, add 1 to account for our current step, and commit that finalized score straight into our memoization table before passing it safely back down the call stack. Let M be the number of rows and N the number of columns in the matrix. Time is O of M times N. Memoization ensures each cell is evaluated at most once, with up to 4 neighbor checks per evaluation. Space is O of M times N for the memo table, plus up to O of M times N for the recursion call stack in the worst case. Main routine, longest strictly increasing path in a matrix. Read the row count M. Read the column count N. Allocate a memo table of zeros matching the grid size. Track the global best path length. Try every row as a starting point. Try every column in that row. Take the maximum over all starting cells. Return the best length found. Recursive helper from row R in column C. If memo already stores a positive score, return it immediately. Best extension from neighbors starts at 0. Check all 4 adjacent cells. Only recurse when in bounds and strictly greater. Keep the best child path length. Store 1 plus the best child as the score at this cell. Return the memoized score.